of Worship, presented by Kurt Friedman. This session is being recorded. We ask that you kindly mute your device and keep it muted during the presentation. Please post your questions in the chat in real time. Where possible, Kurt will try to answer your questions during his presentation. Following the presentation, there will also be time for a Q&A. Prior to turning the session over to our presenter, I'd like to share some information about him. The president of CMF Engineering, Inc., Kurt Friedman, is an engineering consultant specializing in forensic engineering, mechanical systems design, and energy conservation. He is a graduate of both Lehigh University in Bethlehem, Pennsylvania, and Western New England College in Springfield, Massachusetts, where he earned a Master of Science in Engineering Management. Kurt is currently a registered engineer in 12 states. He is a certified energy manager, certified energy auditor, member of the Association of Energy Engineers, and a LEED AP Leadership in Energy and Environmental Design accredited professional. Kurt is also an adjunct professor of heat pump laboratory, energy management, and alternative energy design at Western New England University in Springfield. Mr. Friedman's professional memberships include the American Society of Mechanical Engineers, the Association of Heating, Refrigeration, and Air Conditioning Engineers, the Association of Energy Engineers, the National Fire Protection Association, the International Association of Arson Investigators, the National Society of Professional Engineers, and the National Academy of Forensic Engineers. Kurt has also published multiple papers and holds several patents. Last year, he received the Best Technical Conference Presentation Award from the National Academy of Forensic Engineers. Kurt is an active member of Temple Beth-El in Springfield, Massachusetts, and Synagogue Council is honored to have Kurt with us here today. Thank you, Kurt. We welcome you, and we welcome all of our attendees to this program this evening.
Thank you for all those kind words. Good evening, everyone. Because of the COVID situation, I wanted to provide guidance to the synagogues for how to better maintain their air quality in their buildings to provide a safer environment and to provide greater opportunities for improved utilization of the facilities.
Ding dong.
I've been working with indoor air quality for more than 20 years and have done specialized work in the use of carbon dioxide as a tracer gas to determine rates of air infiltration in buildings. So without further introduction, we will begin. Indoor air quality, known as IAQ, is fundamental to protect human health for any building occupancy. Rooms of assembly, such as sanctuaries for houses of worship, are especially challenged with COVID to meet expected standards for air filtration, as well as temperature, humidity, air recirculation, treated outdoor air, and energy management. The recommendations that follow include both HVAC technology upgrades and human actions to synergistically reduce the risk of COVID transmission. Such HVAC upgrades must work in concert with a comprehensive plan of social distancing and other guidelines established by the CDC, the Commonwealth of Massachusetts, and other health agencies. I prepared an outline and everyone received a copy of it, and we will follow that the best that we can. We're going to start off with a little bit of review of building mechanical systems, because these types of equipment will be mentioned in the presentation, and this will give everyone a greater familiarity with such technical equipment. Once again, there's many different types of HVAC systems, and your building may have a combination of these systems. And it's important to have an understanding of these because action steps may be different depending on the particular type of equipment that you have in place. I won't mention all these, I'll let you read down them. So it's important that you have an understanding of the inventory of different types of HVAC systems in your building. There's some fundamental aspects to providing ventilation in the building. We have what's referred to as an air handler. Air handler can circulate air, that's this green path. Just circulate air around and around in a room. And then air can be exhausted, or it can be brought in through makeup air louvers to bring in fresh air into a system. We can also have normal infiltration where air actually is leaking through the nooks and crannies of the walls and windows and doors in the building as well. Human comfort is a function of dry bulb temperature, relative humidity, air velocity, fresh air, noise, and pollutants. Human beings require a very finite range of temperature and humidity to feel comfortable. When air conditioning were affected by temperature, and the heat gain into a space is a combination of the heat from people, lights, and equipment, as well as solar gain. When we measure air flows in the building, we use a multitude of different types of equipment. And we can see some featured on the table here. I'll hold some up to the camera. Here's a velometer. This is a velocity probe, a velocity grid. And here's the instrument that's used to measure air. Now, this device cost about $4,000. This device is about $100. So if you want to measure some of these airflows, you can get some of these devices that are most affordable for you, or hire a professional. Here's an anemometer. It's a flow hood to measure airflows through a supply register. And here shows a technician with a velocity probe and a velocity grid. Adjustments can be made with an adjustable sheave with a motor, so it's like a multi-speed bicycle. You change the pulley ratios and it changes the fan speed, which changes the amount of air which circulates. We can also use what's called a variable frequency drive. Think of it like a dimmer for a light. It electronically adjusts the power frequency and adjusts the speed of a motor so that you can adjust the airflows. These are very popular and very cost-saving. Of course, maintaining equipment and working with an HVAC contractor is vital to keeping your systems in proper operating condition. This is a hydronic system on the left. This is a power burner on the right. It's a gas furnace, oil-fired furnace, electric furnace. Just shows ductwork. Once again, HVAC systems can be complex. Some can be more involved than others. When we talk about infiltration, there's a term referred to as ACH, air changes per hour. A tight home, for example, will have an air change of about a quarter of a volume of the house is changed per hour. Average is about half per hour. And something with high leakage is 1 or greater. This shows a distribution of residential infiltration. Once again, about the median is about half an air change per hour. So your buildings, once again, many synagogues were built just after World War II. And so based on the age and methods of construction, your rates of infiltration may be different. Typically, we'll look at the heat load of a building, and we look at all the different components, the doors, the windows, the roof, the walls, and we can mathematically model these. Cooling systems can be chilled water, expansion, or they can just bring in fresh air. We call that economizing. Your Your duct distribution systems are made up of blowers, dampers, grills, they can have heat exchangers, control systems. Older buildings might have steam radiators still. Hydronic or circulating hot water systems are also fairly common. We have baseboard heat. These are called unit ventilators, very common in offices and classrooms. This is a hydronic boiler, oil-fired, and this is a gas hydronic boiler, wall-mounted. Heat exchangers can be used to set up additional loops in buildings or to transfer energy between systems. We'll talk about this. If you have to set up a secondary loop to avoid systems from freezing, you can isolate systems with glycol using these plate heat exchangers. You can have large industrial boilers with power burners. Rooftop units are common. They can be usually natural gas or propane, and typically have expansion cooling. Right here, this is the intake air for this rooftop unit. And these dampers here are used for economizing or to introduce fresh air. Hydronic heating or cooling using circulating chilled water or hot boiler water. Central chillers is an air-cooled central chiller, and here's a water-cooled central chiller. So your building may have one or more of these types of mechanical systems. Maintenance and commissioning is also very important. And I'll just highlight some of the comments here. HVAC mechanical systems should be recommissioned at least once each year for both performance purposes and also for energy conservation and cost reasons. If systems are not running properly, you will pay more in utility costs. And also in Massachusetts, where during the colder weather months, we can have temperatures of 0 or even 10 below 0. Some of the membership has facilities even in the state of New Hampshire. We have to be wary of this, and especially when we're calling to bring in more outside air into facilities, you have to take steps to install antifreeze to prevent systems from damaging themselves. So I'm calling for, if necessary, use plate heat exchangers with secondary loops. ASHRAE Standard 180 is a standard practice for inspection and maintenance of commercial building HVAC systems. And we'll just highlight a couple of these. But anyway, the purpose is to establish minimum HVAC inspection and maintenance requirements that preserve a system's ability to achieve acceptable thermal comfort, energy efficiency, and indoor air quality in commercial buildings. This standard might be a basis for your performance contracts with your HVAC subcontractors. And just a couple here, and there's many, but basically it's a system check of your system to make sure that things are functioning properly. One of the reasons for coming forward is that based on the Massachusetts COVID guidelines, I felt that there was a lack of engineering specificity. Whereas there are guidelines, but then the question is from the engineer, well, what do we do next? How do we take these guidelines and implement them so we have successfully operating systems? And here are some of the guidelines here. Occupancy, including staff and clergy, 50, and also the rest of the congregation. 50% of the building's maximum permitted occupancy, up to 10 persons per 1,000 square feet, and that's per enclosed room. So you only 10 people per 1,000 square feet. So if you had 500 square feet, that would be 5,000 square feet, that would be 50 people. And then the other statement, this is verbatim right from the Massachusetts guidelines: promote ventilation for enclosed spaces where possible. For example, consider opening windows and doors to allow airflow. Well, this might have worked later this spring and this summer when temperatures are certainly very moderate, but this will not work when temperatures get very cold, which happens each year in New England. And so if we have temperatures, 30, 20, 10, 0, you're not going to be able to successfully open up windows and doors and maintain comfort. So what to do? Now, the other factor here, because the HVAC upgrades cannot manage COVID by themselves. We still need to maintain proper social distancing and follow the other guidelines established by the CDC. And principle on that is to wear masks. Now, the Massachusetts guidelines do allow medical exemptions, and also exemptions for children 2 to 5 and 2 or younger. I'm recommending that there be no exemptions in order to protect the health and safety of everyone present. And should someone not be able to comply with the use of a mask, they do have the option of viewing typically online. So comments on masks. N95 and surgical masks should be encouraged. Bandanas and gaiters should not be allowed. Face shields without masks should not be allowed. There should be no medical exemptions. And the next slides, I think, will substantiate this point of view. This is a study that was done in 2018 on the performance of various types of masks looking at volcanic ash with particle sizes of approximately 2.5 micron or less.
Art, there was a question.
Go ahead.
It was about occupancy limit. The
Mhm.
question is the occupancy limit 1 person per 1,000 square feet or 100 square feet?
It was 10 persons per 1,000 square feet for each room. So for example, if we're talking about the sanctuary, 10 persons per 1,000 square feet of the sanctuary, that's the total square footage of the sanctuary, including aisles and bima and any other parts, not just the seating area, but the entire sanctuary. But it's not for the entire building, it's for each room. For a classroom, it's based on the square footage of each classroom.
So we can understand that to be 1 person per 100 square feet then.
100, yes. Mhm.
Thank you.
So here's the N95 mask, which performs the best, and here's the bandana, which performs the least. The filtration efficiency is near 100% with an N95, and only maybe in the 30 or 40% for a bandana. Here's another study done in 2010, comparing the performance of an N95 mask, a surgical mask, a bandana, and a pre-shaped face mask. So here the bandana, only about 11%, a simple face mask, about 6%. And the idea is that the face masks not only protect the user of the mask, but if a person happens to be a carrier or they're sick, their virus particles will not be admitted out into the air nearly as much.
So that someone asked, I thought that the guideline was 8 persons per 1,000 square feet.
8 persons is for a classroom, a sanctuary, and I'll show you the different types of use. We'll be covering the sanctuary, offices, and classrooms. And the standards are different for each.
Thank you.
Then there's Massachusetts guidelines for entering and exiting. And what this does, basically, it asks that the synagogues establish a plan. People just can't randomly come in and leave. It should be done in an organized sequence to maintain social distancing and prevent people from having to basically cross paths. And also avoids people from standing in line next to each other. ASHRAE Standard 62.1 has long been established to provide the quantities of fresh air that are required in the different types of occupancies. And these standards have changed and evolved over the years to both maintain comfort and health, and also with considerations towards energy conservation. CO2 at the concentrations commonly found in buildings is not a direct health risk, but carbon dioxide concentrations can be used as an indicator of occupant odors and occupant acceptance of these odors. At the activity levels found in typical office buildings, steady state carbon dioxide concentrations of about 700 parts per million above outdoor air levels indicate an outdoor air ventilation rate of about 15 cubic feet per minute per person. And that's based on a person doing simple activity, like coming to shul or reading or studying. The new ASHRAE standard calls for only 5 cubic feet per minute per person plus 0.06 cubic feet per minute per square foot of that space. For example, if you have 100 people in a 2,000 square foot space, 100 persons times 5 CFM per person is 500 CFM. 2,000 square feet times 0.06 CFM per square foot is 120, a total of 620 CFM, or only 6.2 CFM per person. And here's some examples. So here's a modern theater, and new seating is bigger. And so we have about 7.3 square feet per seat. Older styles, which are probably very common in many of our synagogues, it's only about 5 square feet per seat. So people are physically closer together than in a new theater. Here's the floor plan at my synagogue, Temple Beth El. And these blue dots that you see here are those areas which I've designated as seats that are acceptable to meet the social distancing requirements. Some explanation here, you'll see these seats here, they're spaced. The seating is every 3rd row, where these seats are every other row. And that's because these seats are closer than 3 feet together. So every other row would be too close. We have to go every 3rd row. These seats, which are 3 feet apart, we can go every other row. So you can see that there's many seats that can't be utilized. And down an aisle here, I didn't have people seated here because someone walking by would make them too close. So you end up, when you apply the social distancing criteria, there's many seats that you're not able to use. So there are about 108 seats of 466 shown on this diagram.
And the clustered dots indicate families?
Yeah, so we did this to basically create family units. So the usher would say, okay, I have 2 people, but you can put 2 people where there are 3 because that's the cluster that's available. Think of a waiter seating people at a restaurant. So you could have a table which could seat 4, but there's only 3 people in that party. So the table would only be able to receive 3 people, even though it could potentially receive 4. And you could have other options. So based on the reality of kind of the randomness of family sizes, you're only going to fill perhaps 50 to 75% of this 108. So once again, you have ultimately less people who are able to be seated. So you might end up with perhaps 10%, maybe 15%.
And someone's asking, does this assume everyone is facing forward all the time?
It's based on the seat. Now, in this arrangement, people are facing forward. But you could have other seating arrangements where people maybe are in a circle or facing each other. But the same social distancing requirements would hold true. And different shuls are designed differently. Bethel has a very large bima, so the proportionate area of the bima and the hall and the aisles may be greater than other facilities. So it's a combination of fixed seating and freestanding chairs. And here's a entry and egress plan that's been established. And once again, we have 9 sections, and we have the different family pods and stuff. So everything's mapped out. So if you're receiving reservations, you would receive the reservation as a single person, 2, 3, 4, 5, and then you would then complete your invitations, the reservations based on your available seating. So you want to do this ahead of time. People simply just can't line up at the door and pile in. It needs to be done in a logical way so that the different sections are filled, so you can try to accommodate as many people as possible. So in this case, there's 30 separate family units that are designated here, ranging from 2 to 7 people per pod.
And your capacity in that room was 466, is that correct?
Yes.
And yet, under these conditions, you could seat 108 people.
Maximum, plus the
Thank you.
clergy on the bima.
Right.
So once again, it takes planning and organization. And so the actual square footage is about 7,000 square feet. So it would give a potential of 70 people. And 50 or 60 is realistically about the maximum that we could do. So offices are also 50% of the maximum permitted occupancy, up to 10 people per 1,000 square feet, or 1 per 100 square feet. And the guidelines also call to open up windows and doors to increase airflow where possible. But when cold weather settles in, where you have temperatures of 20, 10, 0, or even below, not going to be able to achieve that.
There were some more questions
Go
about
ahead.
the earlier slides. The first was, I thought that all people have to face the same direction at meetings and meals during gatherings.
Well, this is the given seating. Now people are just facing forward, and there's adequate social distancing. But just based on the seating, people are not in the same direction. It's but appropriate social distancing is being provided.
There's another question about singing. How do you factor in singing, or do attendees not sing?
It's been suggested that people sing quietly, and that's another reason to have an appropriate mask, because having an N95 mask will keep particles much better contained.
And one more, what about air purifiers?
We will get to that subsequently.
Thank you.
So the standards for offices are actually the same as sanctuaries. 50% of maximum 10 people per 1,000 or one person per 100 square feet. And what's a mandatory use of face masks? Schools are different. Schools is 40% and up to 8 persons per 1,000 square feet, or 0.8 of a person per 100 square foot. And once again, improve ventilation from closed classrooms, clinic areas, and other enclosed spaces where possible, open doors and windows. Now, a sanctuary is going to have, or may have, a much more involved HVAC system, but a typical classroom may only have a window or a simple unit ventilator or a simple heater. And so this needs to be thought of more carefully. And once again, mandatory use of face masks. And a face mask is really your best defense. Once upon a time, we went to beautiful theaters surrounded by hundreds or if not thousands of people. And hopefully someday that will return. The engineering that goes into a large room of assembly is actually quite complex. I'm going to just very quickly present the theory that goes into the analysis that we'll be showing you, just so you understand the details that have gone into this. This methodology is one that I've developed myself. It's based on science, and I've developed this over about the last 15 years. And it has a wide range application to many different types of air quality considerations. What we have here, it's a continuity of carbon dioxide. Carbon dioxide is not destroyed, it's preserved, and so we have incoming fresh air, we have exiting air, and we have incoming carbon dioxide from people, all contained within a room volume. So what comes in, goes out, and is diluted. And once again, there's a lot of science to this, and I just want to share with you the potential for this science so that you can see that you can understand the detail that went into this evaluation. So there's a long established relationship between how much a person breathes and how much carbon dioxide they expel based on their activity levels. From sleeping to prayer, studying, driving a car, or sprinting around the block.
So speaking of activity levels, there's a question about air safety in restrooms without windows.
Air safety in restrooms without windows.
Yes.
But the restrooms would therefore be expected to have an exhaust system.
Would the occupancy rate decrease in such a space?
Repeat the question again, please.
In a restroom that has no windows, would you recommend reduced occupancy?
Generally, the rate of exhaust is 75 cubic feet per minute per bathroom stall. Some people feel that people should not be using stalls adjacent to one another. I think that's reasonable. This is a detailed mathematical model, so all the various parameters are carefully listed. There's nothing left for the imagination. Everything is carefully detailed and itemized. Just kind of. And this presentation will be distributed afterwards. Okay. So I have some examples. So we take that theory and apply it to different situations, and the idea is so you can see the effects of this. So here we have a small enclosure. This might be, if you're standing out and waiting to vote for hours on end tomorrow, you may be wanting to get a device like this to shield you from the elements. So obviously a very small enclosure. So if you are sitting in here and you're only having ventilation of 3/4 of a cubic foot per minute, normally when you're breathing, you're about half this rate, about 0.35 CFM per minute when you're at rest. You can see the carbon dioxide levels get very, very high. Just anything over 1,000 is clearly not recommended. And so this goes into levels which actually are approaching a kind of a danger point. Everything, maximum exposure limits are recommended at nothing above 5,000. And so here's one at 3, and here's 15, which keeps you at about 900 parts per million. So there's an example. Here's another example. This is a mansion with a room 25 feet wide, 40 feet long, and 20 feet high, about 20,000 cubic feet. So the red line is if there's no outside air at all, and the blue is 15 cubic feet per minute per person, and the green is 30 cubic feet per minute per person. So not only does it give us the quantities in terms of carbon dioxide concentration, but it does it in real time. So here's hours down here. The other one up here, you see how quickly this quality of the air deteriorates. So if you are in this booth within 15 minutes, you have unacceptable air quality. You might want to think about this next time you go camping in a tent. Okay, the basis of the proposed ventilation rates, 10 to 20% occupancy, at 10 to 20% occupancy, outdoor air flow rates can be increased to provide more fresh air per person. If systems were designed for 6 CFM per person, that's the present ASHRAE standard for a room of assembly or house of worship sanctuary, the systems should be able to provide 6 to 7 times the outdoor air at 15% occupancy. The idea is, and this is not magic, is that if a sanctuary was properly designed for full occupancy with 6 CFM per person, then we should be able to increase that to roughly 40, 45 CFM per person at 15% occupancy. And that's the typical occupancies that we are expected to see when we follow the COVID guidelines. But you do need to determine what your maximum occupancy is in your sanctuary, or your classrooms or offices. You need to determine the maximum cooling capacity, the maximum heating capacity, and then if your system is able to meet the energy capacity requirements, you set the outside air flow rates based on the following criteria. So we're going to want to have an air circulation rate of about 0.75 CFM per square foot plus 25 CFM per person of that 15% occupancy rate. And you're going to want your air circulation to be enabled about 2 hours before the event to bring the space up to temperature. Once again, the air is already clean because nobody's been there. You can have some off-gassing of building materials, carpets, and things like that. So start about 2 hours before, and then you let it run for about 4 hours after the event to basically purge the air in the space. Your exhaust or outside air, once again, want to look at setting at about 45 CFM per person and controlled by a carbon dioxide controller. All right. Let me see this. This is a carbon dioxide controller. Here's my hand. Here's it kind of looks like a thermostat. Now these are set up inside That's the carbon dioxide sensor. And then you hook up your wires to this, and this carbon dioxide controller would activate a relay, which would turn on an exhaust fan or activate the automatic louvers inside your air handler to let fresh air in or allow air to go out. So it's an automatic device. We also have carbon dioxide monitors. It's another carbon dioxide monitor. And here's another monitor. So you're gonna wanna have both a controller and a monitor so you're able to confirm that your systems are working properly and to have some assurance that you're getting satisfactory or maintaining satisfactory air quality. So this gives you that feedback in real time so you know that the measures that you've implemented are working properly. Now, the use of...
Question, there's a question.
Go ahead.
45 CFM per person at 32 degrees Fahrenheit into a room at 70 degrees Fahrenheit means you need to add 500 watts of heat per person to warm the cold air in room temp, the cold air to room temp.
The air would be preheated inside your air handler. Air handlers are designed to temper the air coming in, and in the summertime also cool it as well.
Your heating system has to add that heat then.
Right. Now the heating system
Right.
should be designed for that. If it's, if it was rated at the nominal 6 CFM per person, which is the ASHRAE requirement at full occupancy, then at 15% occupancy, once again, we're not calling for any more outdoor air to be introduced than was previously designed by code.
You just got to make the system run harder. I understand. Okay.
Right. It'll run, the amount of makeup air will be the same or similar to what it would be if the space was fully occupied.
All right. Okay. It's an enormous load, but yes, I understand.
Now, there's some other things that could be done. You could put air-to-air heat exchangers to reduce some of that load. You could add, put in a dedicated makeup air unit. So there are some things, but the idea here is that winter's coming. People want to know what to do. So in this way, you could use your existing systems, assuming that they were designed properly, to run to meet an occupancy load of up to 15%, which realistically is about as much as you're going to seat based on the COVID standards. Now, based on your specific system performance, your peak occupancy could go up or may come down a bit. If you find that you don't have enough heat capacity, you may be able to only do 10% instead of the 15%. So you have to make this decision. And also it's a function of what's the weather conditions going to be. If it happens to be only 30 and it's not 0, or when you get to the very extreme winter weather, late December, early to mid-January, you know that, hey, we just can't do more than 10% if it's less than 10 degrees outside. So there's got to be some engineering calculations run to determine what your capacity can be during certain types of weather conditions.
You'd also want to put a carbon dioxide controller on the flapper to adjust the flapper for the amount of people that's in the room.
Yes, and so you're going to adjust it so that you only need to bring in the amount of air based on what your 10 or 15% occupancy is.
Right. So we have to install a sensor and a controller and some way to actuate the valves with the
Right.
flappers if they're not already motor controlled.
Yeah.
Okay.
Commonly, the systems would have an actuator in place, but maybe that actuator has failed or broken down, so you need to restore it. So anyway, the cost, these controllers run about $350 plus installation. And then if you need actuators, repair on your louvers, or if you need to install an exhaust fan, obviously that's additional cost. I would say though that this same technology can be used even when COVID is no longer here. It can be used to manage airstreams and conserve on energy. Because if you many times people will keep louvers open somewhat, 10 or 15% open. And so you're always introducing fresh air even when nobody is present. And so you want to base these on providing quality air when you have occupancy.
Thank you.
So with the use of automatic devices and with Jewish tradition, some have asked questions about, do these automatic controls create any ritual questions? And they can. And by themselves, they would. But there's a Jewish principle of pikuach nefesh, whereas if technology is necessary to protect or save human life, then it is allowed, because it's kind of fundamental. So here we, in order to maintain air quality to protect people's health, this device and the automatic, the other mechanisms are necessary to protect human health. Some people liken this as very similar to a thermostat, which it is, but it's very purposeful to maintain adequate air quality. So these type of questions certainly can be discussed with your ritual committee and your rabbi.
There's some more questions about air quality.
Mhm.
What happens if you have a system that only recirculates air?
Well, then the only fresh air you have would be the naturally occurring infiltration. That's air coming through the nooks and crannies of the walls, the windows, the doors. It would likely not be satisfactory. So you would have to install some type of exhaust fan so that you're pulling air out of the building, and then fresh air would be introduced through the nooks and crannies. You also would want to make sure that your heating system would be able to warm the place sufficiently. And so there would have to be an evaluation. You may have to install a dedicated makeup air system. You may want to evaluate it and determine that, well, we'll be okay down to maybe about 25 degrees Fahrenheit, for example, but below that, we're not going to keep up, or it's going to get very cold. So there would have to be an engineering evaluation of that building space to determine what it can and can't do, or how you could best accommodate it. But you do need to bring in ample amounts of fresh air to maintain air quality.
And what if you just have windows and radiators?
I would recommend the installation of ceiling fans so that you can circulate the air. So when air comes through the windows, it gets mixed with the room air. And then you could use a carbon dioxide monitor, but you're going to want to evaluate that. And based on the chart, you're going to stay about 550 to 600 parts per million. Above that, then you're going to have less airflow. So by looking at this study, we're able to equate air changes per hour through carbon dioxide levels. And the standard of 1,000 parts per million carbon dioxide, others have recommended reducing that to 800 to improve the air quality. And I'm calling to reduce that to between 500 and 600 parts per million to make it even better, so that we're increasing the airflows to the maximum level based on the full occupancy that they're originally designed for. And so I'm calling to increase the airflows to the maximum expected airflows that that space would otherwise have been designed for. There may be no upper limit, but I wanted to take steps to maximize airflow to minimize risks. At the same time, following the other standards, social distancing, and the use of masks. On the left, this is the same carbon dioxide monitor, and on the right is a carbon dioxide controller. So here's some examples. There's a sanctuary. This happens to be Temple Bethel in Springfield. So on one axis here, we have carbon dioxide concentration. And the red is if you do nothing. So the question was, if you don't have makeup air and if you didn't open windows, you would have your carbon dioxide levels increase dramatically. So within about an hour and a half, you're at 1,000 parts per million. And these ceilings here are about 35 feet high. And then the brown, that's the present ASHRAE standard. So you're at 800 parts per million, also at about an hour and a half, and you exceed 1,000 parts per million after about 3 hours. Now the ASHRAE standards for houses of worship, I mean, there's some faiths that have services that are only about an hour, and you can see after an hour, you're okay. But services that go longer, and commonly Sabbath services, and certainly high holiday services, go well beyond. And so the blue curve is what I'm calling for. That's the 45 CFM per person. And we hover just above 500 parts per million. Here's another example. Once again, this is applying the ASHRAE standard of 5 CFM per person and 0.06 CFM per square foot. And I ran this analysis ranging from 50 people up to 500 people, and presuming 500 is the full occupancy. And so the red is 50 people, which is 10% occupancy. And after 3 hours, we're up to 700 parts per million, still reasonable. But at full occupancy, look at the blue, my goodness, within, at a half hour, over 1,000 parts per million. And after 3 hours, we're at 1,600 parts per million. So in the business, we call this a sensitivity analysis, and allows us to compare expected results. And you can see this is quite dramatic. And my conclusion from this is that the ASHRAE standard, even without COVID considerations, is grossly inadequate. Another way of looking at it, I developed a parameter called particle concentration factor. So when we start off, we're at 0, and we have the different scenarios. How do they compare against each other? And so the do nothing with bringing no area, and that's the red one, you can see how it goes up. And then here's the brown, which is the ASHRAE standard. And then here's the blue, which is the standard that I'm calling for. So there's an obvious significant advantage or improvement. And this kind of non-dimensionalizes it for any room size, for any type of occupancy. And it allows a fair comparison between any different room or space. And so this provides kind of a basis for a conclusion with the recommendations that I'm calling out. And this is also done with a theory that I developed. It allows such a comparison. Okay, some of the tools that are used. The MERV 13 filters work. They effectively filter out virus particles in the range that we're talking about with COVID, also conventional flu, also conventional cold. And you can see on the chart, so this is a human hair, and these little red dots here, those are the size of the COVID particles. Here's some sand in comparison. So the MERV 13 filter is a specialized tool that does a job. A conventional household filter is not able to do this. And this is why these filters are in such demand. That's also another reason why I wanted to give this presentation, because there's many entities that simply cannot get MERV 13 filters, or their HVAC systems cannot accommodate MERV 13 filters because of the pressure drop, or because their filter racks can't accommodate those filters. And so what can be done? What can be done is to maximize your ventilation rates as best you can based on the capabilities of your existing systems to minimize risk, and to maintain social distancing, and to use N95 masks. So this shows some performance. So the MERV 13 filters will filter out 90% of particles between 3 and 10 micron, 85% between 1 and 3 micron, and 50% between 0.3 and 1. So aerosols are considered anything to be 5 micron or less. So the MERV 13 is an effective tool. It's been long established to be effective.
Here's a question.
Go ahead.
What if your RTUs were not designed for use with MERV 13 filters? I was told ours could not handle those due to the restrictions in airflow.
You need to evaluate that. Some can, some can't. You might have space constraints. You might have to have a sheet metal contractor modify the filter rack so it can take the thicker filters. And it depends what kind of system you have. Like, for example, if you have steam coils or if you have a hydronic coil, the restricted airflows will not hurt those air handlers. If you have a gas furnace and the airflows may be partially restricted because of the ductwork, you could have a situation where your furnace will overheat because the air is so restricted. It needs to be evaluated on a case-by-case basis. It's not all yes and all no. So you may want to look into that in more detail. You may want to measure the airflows and measure the pressure drops more carefully to see if it can accommodate that. For air conditioning, if you have a DX, or we call it expansion cooling coil, if you have restricted airflows, you could see your air conditioning coils freeze up. So the solution is, instead of setting your thermostat at 72, you may have to settle for 75 or 76, so the greater temperature will prevent the coil from freezing up. So once again, you have to look at that on a case-by-case basis.
And if the HVAC system can efficiently only use MERV 8, is there any utility in using a system like the L-Wave system? And that could be I-Wave system.
Some people have increased to go to a higher MERV, which will do something, but not a lot. The effectiveness of MERV 13 is much better. So to get the effectiveness, also keep in mind that N95 mask provides very good filtration at the source, which is the best place to filter it. So if you're not able to, once again, and if you can't accommodate the MERV 13, you certainly want to have masks, and you certainly want to increase the outdoor ventilation, because those are things that you can do. So once again, the series of recommendations were made here, and the more you do, the lower your risk can be. But the N95 masks, now you can buy these now. You know, in the spring you couldn't get them, but now you can. They're readily available. Through this organization and federation. But you can buy these for about $2.50 a piece. And wouldn't that be a wonderful gift to give to the participants coming into Shoal? They can take them home with them and keep themselves healthier and safer.
The National Association of Jewish Federations has a PPE portal, and we will send you that link with our PowerPoint and other support materials.
There's been discussion of bipolar air ionizers, and There's many school systems that have used these and either swear by them or swear at them. I'm waiting for more scientific opinions on these. I know many school systems, including in my hometown of Long Meadow, have implemented these throughout their schools. The manufacturers have many claims, but I can't speak for them or against them until I see further research papers on them.
Could HEPA filter units be used in closed spaces like classrooms?
They can, and people are doing it. It will do something, but you also need to bring in fresh air to reduce carbon dioxide. HEPA filters will filter out particles and dust, but they won't filter out carbon dioxide. You need fresh air for that. The other issue is that filtering it, and typically one HEPA filter might ventilate a classroom once per hour or twice an hour, but there's no quantification for that. There's no judge of how well that's working or not. It's simply kind of a trust thing. The improvements in air turnover by using carbon dioxide as an indicator are at least based in science. We do know that when people are in confined spaces without adequate ventilation, viruses are transmitted. We do know that when there's adequate ventilation, the chances of transmission are much less. Also, social distancing also helps as well. Once again, there's no guarantees. I can just advise on best practices to minimize risk. Another technology which is gaining popularity is the use of ultraviolet light. Now, there is long established practice of using these, and the ultraviolet light, we do know, works to zap the bugs in proximity to primarily cooling coils. The concern has been when you're running air conditioning systems that the condensation can cause bacteria growth. You get slime. And ultraviolet light is effective at that. But the performance in terms of zapping bugs in a moving airstream is much less. It does do something. It doesn't do anything, but the performance is not as much. It takes a lot of energy because air, although we think it weighs nothing, it actually weighs a lot. And so you have, in order to zap air, you would actually need exceedingly powerful ultraviolet lights. So once again, the primary goal of the ultraviolet lights is to zap bugs in proximity to the air handler, but they may have limited performance in terms of zapping bugs in a moving airstream. Okay, the conclusions. The use of carbon dioxide controllers can be utilized to perform the maximum outside air ventilation based on the HVAC capabilities at design weather conditions and occupancies of 15% or less. And once again, the 15% or less is the expected maximum occupancy that you're going to be able to achieve in a sanctuary based on the social distancing guidelines. Additional mitigation steps include the following: use of N95 masks for all participants, including clergy. I know it may be a bit uncomfortable, but if everyone's going to be protected, those who are leading the service should be wearing masks at all for their own protection. MERV 13 filters, ultraviolet light, limited effect on the airstream, and bipolar air ionization, awaiting further scientific review. Discussion, questions?
This is John over here.
Hi, John.
I've designed HVAC systems, like not for houses, but for chillers and stuff like that. So I'm also the house chairman of Temple near Timid in Peabody.
Mhm.
So I've been doing some work in this space. So you've chosen CO2 levels as a metric for air quality. Does that correlate well to COVID-19 exposure risk, or is that a metric? How did you decide to drop the levels from 1,000 and 1,200 down to 500? Where did that number come from?
500, what's it? It comes from based on the maximum expected occupancy of a sanctuary of about 15%.
So it's what's achievable if you take the existing air system and go to 15% and
Right.
crank it up to do the best you can get down to 500. So it's more of a limit based on your calculations than a number that would be safe for COVID exposure. So
Well, there are some virus transmission is a function of distance. It's a function of concentration of particles. There is some analytic to that. The idea here is to minimize risk.
Mhm.
Also, I mean, we all go into supermarkets and hardware stores and other retail, and I've observed carbon dioxide levels which are much greater. So if we are typically background levels, that's based on background levels of about 360 parts per million. So it's a metric that's used to, first of all, to provide feedback. Because once again, if you simply put filters on, I think we all know that you could have, even if you put in MERV 13 filters and they shift in the rack, or they collapse, or they become wet, and they and now you have a gap. Well, they're going to allow a bypass of air to go past them.
Yeah, close to these
by-
classrooms. so to
By
speak.
diluting the air as much as possible, and be able to do so in a controlled method that will carry you through the winter is the best approach that I can think of, along with the social distancing, and also along with the use of N95 masks to minimize any potential for the emission of virus particles into the air.
Your recommendation is basically crank as much as you possibly can with the existing system to make the air quality as good as possible. You're not speaking about any correlation to COVID exposure at all. This is just best practice right
Yes.
now.
Yes.
I see. Okay. We have, maybe some of the people have Hebrew schools where we have small classrooms which are enclosed spaces, and the 45 CFM per student in those rooms, like I said, it'd be 500, 500, about 500 watts, just doing a quick calc, MCP delta T, right? So it's about 500 watts per student, basically. If we have 6 students in the class, that's a lot of power, 3,000, watts. So we have
At what ambient temperature?
like 70-degree ambient temperature and 32 degrees outside.
Mhm.
So, that's a lot of power. So, like you can't even plug in wall units to make up that heating. We have baseboard in the school. We don't have, like active HVAC running in those rooms. So we're kind of hoping that for the winter months, we have to close the windows because the heating system will never keep up. And you can't even plug in heaters. I don't even think we have to get an electrician in there to rewire the outlets for the power consumption. So we're trying to do something along the lines of a HEPA filter. It's 99.7%, good down to 0.3 microns. And we're looking at something that can give us 6 air changes per hour, basically looking at the room itself, 300 CFM coming out of the beast, out of the filtration unit. We're kind of hoping we could do something like that. So obviously the CO2 levels is something I hadn't considered before. So this is great feedback. But do you think that you're saying that those units basically have no scientific validation that they can actually filter out or be effective against preventing COVID
A
transmission?
true HEPA filter does filter out fine particles. A true HEPA filter. So is what you're using a true HEPA filter?
That's what we're sourcing right now. We're looking at alternatives right now, and we're looking at the HEPA filters. Not so much the ionizing radiation or UVC. Again, I think the same thing you're saying is that it's hard to zap bugs that are moving fast. Takes a lot of power. And the ionizers could introduce ozone potentially into the air. So we're looking
Yes.
at strictly a HEPA filter unit.
The ionizers, the ozone issue has been identified because the ozone is a respiratory irritant.
Right.
And some people have said, we're just not going to use it because we want to have a do no harm type of approach.
Mhm.
And it's better not to use those because even if they are successful, you're still going to create another problem.
Right.
So on the, if you have other heating systems, if you're able to exhaust the air out of those classrooms just to have some true air turnover. But once again, the virus is transmitted and what kind of distances are you having in the classroom between students?
Yeah, the kids are basically, their chairs and their desks are at least 6 feet apart, more if we can. The rooms are 20 by 20, and there's probably about 6 students. Actually, so we're probably violating the standards per classroom.
And how many classrooms do you have?
4. Well, we have like 6, but we've basically done every other room to try and split them all up more or less. We're using 4 of the 6
I mean,
or 7 classrooms.
If you could put some exhaust fans, position them in the window, and then provide some type of makeup air unit to bring in temperate air into the building.
Right. But if you're losing that mass flow out, you've got to make it up. You've got to heat it up. That's first law.
I mean,
right?
these are decisions we're going to have to make, but for other reasons, the other potential contaminants besides virus particles, as you know, moisture. I mean,
Yep.
One of the key components of human respiration is water vapor.
Right.
And so you need to exhaust that. The HEPA filter is not going to remove water vapor. The HEPA filter is not going to remove carbon dioxide. So you need to maintain, I'd say at least minimum ventilation rates that are non-COVID. So even if you feel comfortable treating the COVID particles with the HEPA filter, you have the other components of the products of human respiration that need to be treated based on present code.
Right.
Okay.
So that
So
0.7.
you need to at least meet present code to have any semblance of satisfactory air quality.
Right, it's like 6 CFM per person. I got you. What times plus 0.06 times CFM divided by square feet.
That's for a sanctuary. For a classroom, I think it's a bit more, but we need to look at that. So you still need to provide for ventilation. Now, so what's the primary heat in these classrooms? Is it a radiator? Is it a perimeter? What do you?
Baseboard.
Just
Yeah.
baseboard now. I mean, what was common is to use unit ventilators, which bring in outdoor air and heat. I really think that, and there's still time, it would be to look at an upgrade in your classrooms for
Very
everybody's
expensive
better.
upgrade.
I mean, the cost of getting sick, or if a child gets sick and brings it
I
home.
understand.
Yeah, yeah.
You're right. You're right. I shouldn't be talking money, but yes. Okay. All right. Thank you. Yeah, I'm sorry to take up your conversation.
No, that's what we're here for, is
Right.
to resolve these issues.
Mhm.
All right,
Also,
Sharon has a question.
Go ahead.
So Kurt, I was the one that asked about the iWave system. It's a new system that apparently takes the, that changes the molecule, takes the hydrogen out of it and sends it through the filters. And
I'm not familiar with a particular, but is this some type of ionization system?
I think it's related to an ionization system. But that's, I asked the question about the MERV 8 system, and our HIVAC people suggested that we look into that at a cost of like $1,300 per our 2 HIVAC units.
The performance values that I've seen for MERV 8
Mhm.
will only take out a fraction of the small particles.
Right, that I understand.
Okay, and that's as an aerosol. Droplets, sure, but the aerosols, which are the 5 micron or less,
Mhm.
you really need MERV 13.
Right. So this device that would be attached to it, in your opinion, wouldn't
The
do the-
ionizer, I'm not familiar with that particular unit, but if it's an ionizer,
Mm,
the other components which are released into the air can be irritating to the lungs. That's been demonstrated, and some people are advising against it. I'm waiting for more published literature on it because I'm an engineer, I'm a scientist, so I'm looking for others to do it. And once again, we need to be careful, and that's why. So what can we do? $2.50 a piece. Everybody gets an N95 mask. That's your best air treatment from, okay? And then to dilute the air with ample amounts of fresh air,
mm.
you know that's going to help.
Okay, thank you.
Any other questions this evening?
I like the suggestion about the N95 mask for everybody. That's, yeah, this way you're wearing a filter right on your face, right? So, well, that's a great suggestion. Thank you. We have to save money, honestly. I'm sure we're all in the same situation. Nobody's flush with cash, but we want to do it safely, of course. So I appreciate that.
I mean, I would, for children, what's it, $2.50 a piece? I mean, they can be used more than once, but I would expect that if an appeal went out to your membership, I think you'd get donors. People would buy a box of them. They typically come in boxes of 40, $100 for a box.
Meet once a week. That's the cheapest solution, and it's probably one of the safest too, right?
Right. I mean, for classrooms, and once again, I know, I mean, everybody's expected to wear masks, and those who can't, I guess there's remote learning. But I think with the uptick in frequency of the virus now, where there's a greater chance of somebody in the room having it, we all need to take steps to minimize risks, because we value our networking opportunity to be in person. I teach at Western New England University in Springfield, and everybody wears a mask, not only indoors, even if you're outdoors on campus, you're expected to wear a mask, and everybody's abiding by it. And that's really the only way to keep open and keep safe. Also at Western New England, they do have carbon dioxide controllers that they haven't had in place. Once again, this is a very common technology. I've been using it for more than 2 decades, but there's many schools, universities that have been using them. I've been informed that the NFL is using them in all their practice rooms. It's a tried and proven technology. Perhaps, pun intended, this technology is not filtered down to other commercial entities like houses of worship, because maybe they didn't want to spend the money, or they didn't want to have something else to maintain. But now's the time. It's a tried and proven technology.
I'm not seeing any more questions. Randy, did you have a question?
I was going to just say that I think the governor has now reduced the amount of people that can be inside a house of worship. I was seeing it going across the screen. I was watching the news, so I suppose everybody should be on the lookout for that starting Friday.
Thank you. We'll definitely look for it.
Thank you very much.
I'd like to thank Kurt for his incredibly detailed and informative presentation. You provided so much for us to consider. I'd like to thank all of you for joining us this evening, for sharing your thoughtful and courageous questions, and for your hard work for your synagogues. And I'd like to bless you with good health if I could, but to wish you all well and to have a good night, and please stay well.
Thank you. We really appreciate it. Very nice. Thank you so much.
Feel free to contact me if you have any further questions. I'll be happy to share all the theory and methodology with you.
Okay.
I'm publishing an ASHRAE on this.
Oh, great. Okay.
We'll include Kurt's contact information in the follow-up email.
Okay. Fantastic. Thank you.
Okay.
You're very welcome.
Thank you.
Thank you. Good night. Erev Tov.
Thank you. Good night.
Thank you. Love the name Ashrei.
Right?